Okay, so in the last video we did some problems with two object problems, still only dealing with specific heat capacity. So today we're going to talk about phase change. So basically up to this point the only equation we've seen with heat has been Q equals mc delta T. Okay, now what it says in the notes is as heat is added to an object, both its temperature and its internal energy typically increase. When you add heat to an object, its internal energy is always going to increase. However, its temperature is not necessarily going to increase. If you think back in the notes about what is meant by internal energy, basically there's two components to this. And the analogy is kind of like mechanical energy, but it's only referring to the atoms or the molecules making up an object. Okay, so basically internal energy is all of the kinetic energy of the atoms or molecules, not of the object as a whole, plus all of the potential energy added together. And again, this is only of the atoms or molecules. We talked about in one of the videos how if you throw a baseball faster, the temperature of the baseball doesn't go up. It doesn't matter the kinetic energy and the potential energy of the whole macroscopic giant object don't matter. What matters is the motion of the individual atoms or molecules. As the individual atoms or molecules are moving faster, they have more kinetic energy. Okay, so when I say kinetic energy plus potential energy, the analogy is with mechanical energy, but they're not the same thing, because this is only referring to the energies of the atoms or molecules making up an object. Now, we also talked about temperature, and how temperature is a measure of the average kinetic energy of the atoms or molecules making up an object. So in other words, internal energy is both of these things added together. Temperature only has to do with this piece. Okay, so you might ask, what does the potential energy have to deal with? Well, that has to do with the state of matter and what we call a phase change. If you look at the third bullet point here, it says, however, when an object is at its melting or boiling point, additional heat does not increase the temperature of the object. Okay, so that means if you take an object that is at its melting point or at its boiling point and you add heat to it, that extra heat does not go into increasing the temperature of the object. And so you can kind of think, let me take this off for just a second. Okay, you can kind of think as you have this box, and let's say this whole box is internal energy. Okay, and again, that has to do with the energy of the atoms or molecules making up an object. Okay, and there is two parts to that. There is the kinetic energy part, and there is the potential energy part. And if I add heat, and again, this is just meant to help you understand the concept. If I add heat, remember that's Q, then that energy can either go to here or it can go to here. If it goes to here, the object is going to have a temperature change. And again, that's because temperature is a measure of the average kinetic energy of the atoms or molecules making up an object. Okay, that's where you have Q equals mc delta T. If that heat goes here, okay, which can only happen if you're at that special melting or boiling point, then you have a phase change. Remember, phase change is what happens when an object experiences a change in its state of matter. So in other words, melting is a phase change, freezing is a phase change, condensing is a phase change. And in that case, we have a different equation besides the mc delta T equation. We have what's called Q equals mL. Okay, so obviously Q is heat and M is mass. What is L? L is what's called latent heat or specific latent heat, depending on the textbook that you're looking at. Okay, so now what we're going to see is we actually have two equations for Q, one dealing with temperature change and one dealing with phase change. And sometimes we use them individually, like up to this point we've been doing a bunch of problems with just temperature change, but it is possible to see problems involving both of these equations either individually or combined with each other. right? And again, what this diagram is basically saying is that when you add heat to an object, either that energy is going to increase in the temperature, or it's going to changing the state of matter of the object. You can't have both happening at the same time. Okay, and so what we're going to do is talk about that in a little more detail for a few minutes and do some basic concept examples, and then in the next video we're going to actually do some calculations with latent heat. So I'm going to clear this for now. Please pause it and jot that down in your notes. Let me know if you have any questions about that. Okay, so I'm going to go back to the slide. On this slide, this is slide 59 in the PowerPoint. It says, in other words, when heat is added to an object, there are two possibilities. Either the kinetic energy of the object's molecules or atoms will increase, resulting in a corresponding increase in temperature, or the potential energy of the molecules will increase, resulting in a phase change. And that's basically what I was talking about before with my diagram. Again, to emphasize, as an object changes from one state of matter to another, its temperature does not change until the phase change is complete. Okay, so if you think of the diagram I had drawn before, the heat can either go to the left side or to the right side. It cannot go to both sides at the same time. Okay, now if you add a bunch of heat to an object, it can eventually end up increasing both sides. But as you're heating an object, either there is a temperature change or there is a phase change. You cannot have both happening at the same time. Okay, so there's a graph, and I would like you to put this graph in your notes. As you're putting this graph in your notes, note the difference between when an object is changing its temperature and when it's undergoing a phase change, and note which phase change requires more energy. And so this is a graph that is made. On the y-axis we have the temperature of an object, and on the x-axis we have heat energy, which is Q. And of course this is T. So what we see here is when we have added no heat to the object, right over here, the object is a solid. As we increase the temperature of the object, we can see, I should say as we add heat to the object, at first what it does is it changes its temperature. And you can see here, between here and here, the temperature is going up. Okay, in other words, for this first section of the graph, the equation that would pertain would be the mc delta T equation. Now eventually the solid reaches its melting point. Okay, so this temperature, whatever temperature you have right here, that is the melting temperature. And as we add more heat, notice that there is a period as it is phase changing, as it's melting. Right in here, we're adding more and more heat, but the temperature is not going up. And that is because during that part of the graph, all the heat is going into the internal potential energy rather than the internal kinetic energy. So for this segment of the graph, you'd be using the equation Q equals mL. Right here, it finishes melting. Okay, so now it's completely a liquid. As we continue to add heat to this liquid, the temperature goes up, 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 up. Here, we get to the condensation point, and it's going to start to boil. And again, the same thing is going to happen during the phase change from here to here. The temperature remains constant, even though we're adding in more heat, even though the internal energy is increasing. It's not increasing the temperature. Okay, so again, here, in this part of the graph, we would be using mc delta T for that part of the graph. This part of the graph would be using Q equals mL. And then this part of the graph would be using mc delta T again. Okay, so you only have the two equations, one for phase change, one for temperature change. And I know we haven't talked a lot about what is L, or what is specific latent heat, but we'll talk about that here on the next slide. I do want you to point out that if you look at this melting freezing segment and compare it to the condensing boiling segment, you'll notice that it actually takes more heat to boil this particular substance versus freezing or melting it. And that's pretty typical, actually. Also something to keep in mind that a solid, liquid, and gas, let's say if you take water, for example, water as a solid is ice. Ice and water don't have the same specific heat capacity. And so it's also true that the specific heat capacity and the latent heat values can change as the object goes from different states of matter. Okay, so in other words, the value for C down here might not be the same as the value for C here or over here in this part of the graph. Okay, but we'll see that later on. So please pause it if you have any questions, jot them down, and shoot me an email. We're going to go on to the next slide. Let's talk more about specific latent heat. So we talked about this before. We know when we hit an object, its temperature will change as long as it's not in the process of phase changing. Okay, that's how we can quantify the concept of specific heat capacity. In order to quantify how heat relates to a phase change, we have this concept of latent heat. And here's the definition of latent heat. You can write that down in your notes. Definitions are important. The latent heat of a substance is defined as the amount of thermal energy required for 1 kilogram of that substance to undergo a phase change. Okay, and so mathematically we write that as Q equals mL, where Q is the heat or the thermal energy needed for the phase change, M is the mass of the substance, and L is the latent heat of that substance. Now, based off of the equation Q equals mL, you should be able to figure out what the units of L are. If you just solve this equation for L is Q over M, and so the units of L would be the units of Q, which is joules, divided by the units of mass, which is kilograms. So latent heat, the unit is joules per kilogram. And again, definitions and units are important. Alright, so what we're going to see now on the next slide is that there's actually two types of latent heat because there's two common types of phase changes. You have melting and freezing, and then you have boiling and condensing. And so you have the latent heat of fusion. It says latent heat of fusion is the energy required to melt 1 kilogram of a substance, or the energy released when 1 kilogram of a substance freezes. And the latent heat of vaporization is the energy required to vaporize 1 kilogram of a substance, or the energy released when 1 kilogram of a substance condenses from a gas to a liquid. So in other words, if we're dealing with a problem, let's say a piece of ice is melting or a piece of ice is freezing, we're going to be doing calculations with the latent heat of fusion. If we're dealing with a problem where liquid is turning into gas or gas is turning into liquid, we're going to be dealing with the latent heat of vaporization. Although it is possible to see both of these values in the same problem, you do need to think through the problem that you're working on and think, am I dealing with something melting or freezing, or am I dealing with a different type of phase change? Also keep in mind that a substance can only melt or freeze at its melting temperature and can only vaporize or condense at its boiling temperature. So in other words, if you take a piece of ice at, let's say, negative 100 degrees and you add heat to it, the first thing that's going to happen is it's going to have a temperature change. You cannot immediately melt ice at negative 100 degrees Celsius because ice does not melt at that temperature. Okay, so first you would have to add heat to get the object to its melting point, and then you would have to phase change. And that's, if we go back to this graph over here, that we can kind of see why that's true from the graph. If I take an object that's not at its melting point, let's say the temperature is down here, as I add heat, the first thing that's going to happen is the heat is going to make the temperature go up, 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 reach the melting point, or the freezing point, and phase change, and then go on from there. Okay, so just to give you an idea of different values for specific latent heat, we can look at this chart. This has some different substances on them: aluminum, ethyl alcohol, carbon dioxide, gold, lead, water. Just look at the values for the specific latent heat of fusion and the specific heat of, the specific latent heat of vaporization. The first thing I want you to notice is that the values for L tend to be very, very high, right? 10 to the 4 is in the tens of thousands. 10 to the 5 is the hundreds of thousands. Okay, so these are much larger numbers typically than specific heat capacity. The other thing I want you to notice, and this is not always true, but typically speaking, again, not always, but typically speaking, you'll see that the latent heat of vaporization is a bigger number than the latent heat of fusion. In other words, what that means is that for most substances, it takes more energy to boil that substance than it does to melt that substance. Okay, so for example, the latent heat of fusion for water is 3.4 times 10 to the 5. That is 340,000. Big number. But if you compare the latent heat of vaporization of water, that's 2.3 million. 2.3 times 10 to the 6. Okay, so in other words, it takes way more heat to turn water into steam than it does to turn ice into water. And finally, we're just going to do some basic examples, and we'll get to the more complicated examples in the next video. Okay, but just really quickly, the latent heat of fusion for lead is 2.5 times 10 to the 4 joules per kilogram. How much thermal energy is required to melt 12 kilograms of lead? Okay, so we're not talking about temperature change here, we're talking about a phase change. So I'm going to be using this equation here. Because I'm talking about melting, I need to use the latent heat of fusion, which in this case is the one that I'm given. But do keep in mind, if I was given the latent heat of fusion and the latent heat of vaporization, I would want the latent heat of fusion because that's the one involving the melting and freezing point. So a very simple question. Q equals the mass, which is 12, times 2.5 times 10 to the 4. And if you just type that into the calculator, you should get 300,000 joules. Okay, so quite a lot of heat to melt this bit of lead. Okay, so that is example 1. And just really quickly, example 2, it says, why is a scald by steam at 100 degrees Celsius much more painful than one by water at 100 degrees Celsius? So I can answer this by basically typing this out. But think about the difference between water and steam at the same temperature. Now, if they have the same temperature, I'm going to do this in red so you can see it actually. If the water and steam have the same temperature, their molecules have the same average kinetic energy. Okay, that's what temperature is a measure of, remember. So what's the difference between steam and water? Why does it hurt to get burned by steam way more than it hurts to get burned by water? Well, the reason is when you get scalded by steam, it's not scalded by steam, the steam also experiences a phase change and releases much more energy. Okay. In other words, with the water, all you have with the water is, let me just type this out, or write this out. You have Q equals mc delta T. Okay, hot water touches you, the water temperature changes. As the water touches your skin and it cools down, it releases heat. That's bad, but it could be worse. Now, what happens with the steam? Well, with the steam, the water touches your skin, and then not only does it temperature change, but first it phase changes as it goes from steam to water, and then once it turns from steam into water, it's released a bunch of energy. It still has to temperature change to reach thermal equilibrium with your skin. Okay, and so that's why it hurts way more to get burned by steam than it does to get burned by water, because the water, all it does, it touches your skin and it temperature changes. The steam has to phase change as well, and this number tends to be very, very big, because remember, in the last, or a couple slides ago, we saw in the chart that the latent heat of water for vaporization is like 2.3 million. That's a very big number. Okay, so if you get burned by steam, it's really not a lot of fun. Hopefully you haven't experienced that, but if you ever do get burned by steam, now you hopefully understand why it's way worse to get burned by steam than it is to get burned by water. So that's kind of a conceptual question. Again, feel free to add that to your notes. If you have any questions, if you need me to clarify about that, please let me know. In the next video, we're going to be doing some calculations with latent heat. And just looking at this equation I wrote down for steam, though, the ML plus MC delta T equation, you should be able to appreciate that these problems are going to get more complicated because now we've added the possibility of phase change. Okay, so in the next video we're going to be doing more complicated two-object problems combining the concept of specific heat capacity and specific latent heat.